So for our final part of this homework, we are actually going to be graphing the situation that is going on with this capillary tube. Essentially, we're going to be graphing it at three different stages. The initial stage, where t equals 0.1 seconds, the intermediate stage, where t equals 60 seconds, and the final stage, where t is equal to the infinite end. There's no end, but infinite seconds. I have it written here as a key that anytime where we need to differentiate H2O and D2O, H2O will be the color blue and D2O will be the color red. Otherwise, it'll just be in pencil. So starting off, a neat thing to note is that the x-axis of all of these graphs is going to be the different positions of the capillary tube. The capillary tube has a divider at 5 centimeters in the initial state, but that divider gets removed. And so from 0 to 5 is where the H2O starts, and from 5 to 10 is where the D2O starts. But that's where they begin to mix. So first we're going to be comparing that to the mass concentration. At the initial state where t equals 0.1 seconds, all of the H2O is on the left side. There really wasn't enough time for both of them to react. This is essentially right after the divider had been taken out. And so the the mass concentration of the water is 1,000 kilograms per meters cubed all across this left side, but at the divider it drops down to 0 because there is no H2O on the right side. The opposite is for the D2O. The D2O is at 0 on the left side from 0 to 5 centimeters, but it rises up to 1,110 kilograms per meter cubed once it hits the right side of the divider at 5 to 10 centimeters. We note that at the intermediate, where t equals 60 seconds, we can see that these are actually beginning to mix together, and we see more D2O on the left side and H2O on the right side, although the densities are still not at their 100% max where we have it here. They're beginning to mix around in there. And the slope is dropping. You can imagine this is just a very steep slope. As time passes, that slope is beginning to become less steep until we hit the final stage, where t is infinity, where the slope becomes 0. And we just have that the density of D2O and the density of H2O is the same across the entire capillary tube. For molar concentration of H2O and D2O, it's a similar situation. We have the molar concentration of H2O as 55.5 moles per liter, and the same is for D2O. It's a little bit less, but it's such a minute difference in this situation. And so we have that in the initial state where t equals 0.1, the H2O molar concentration is at that 55, but it drops down and it's 0 because it has not had enough time to mix. It has not moved over to the other side. Same goes for the D2O. It is a 0 from 0 to 5 centimeters before the divider, but at its side of the divider, it is at also 55 as well. Again, once time passes, once it hits the intermediate of t equals 60 seconds, you can see that this super steep slope, we can just imagine this as a steep slope, ends up kind of decreasing a little bit, and you can see that it's flattening out. You can see that there's more molar concentration of D2O on the left side of that, where that divider originally was, and more H2O on the right side. They're beginning to mix until we hit the point where it is equal across the entire board for H2O and D2O. It's kind of hard to see, but there is a blue line there and a red line as well. For the molar diffusive flux, we know that the maximum molar diffusive flux was 2.78, but we know that for H2O and D2O, they are equal but opposite. So you can see that the H2O's maximum molar diffusive flux hits the 2.78 at the top here, while the D2O's is negative 2.78. And you can see again that that slope is very steep, but it's 0 everywhere else. Why is that? And that's because this is where the divider was. At t equals 0.1 seconds, it hasn't had enough time to move across to the other end. This is the initial state. You can see that once we get to the intermediate 60 seconds, the slopes begin again becoming less steep across the board, and it spreads out further to the ends of the capillary tube. Now, another thing to note is that these two values are not equal to these two. They are a little bit less because at this time, that is where the maximum molar diffusive flux is. This is not where the max is. And again, these slopes will flatten out all the way until we hit t equals infinity, where we hit the equilibrium, and there is no more molar diffusive flux. Everything is evenly spread across, nothing needs to move around. For the mass flux, it's a similar situation. We deduced from question 1 that the mass flux, the overall mass flux, is negative 5.5 times 10 to the negative third. I just wrote the same thing on the top just to have an opposite end for it. And right here you can see it's again very steep at the beginning because there just wasn't enough time for the mass flux to spread across the entire capillary tube. It was just immediately, the divider was only just immediately removed. And you can see once we hit t equals 60 seconds, that slope actually does flatten out a little bit, but also the overall mass flux lowers. It's not as high as it was in the initial state of the divider being removed. And that goes all the way out until we hit t equals infinity, where it is at equilibrium. There is no more mass flux, nothing is being moved, everything is steady and spread across evenly.